Hello everyone, welcome back to my channel. Today we are going to be looking at GCSE Chemistry, Topic 2, Bonding Structure and the Properties of Matter. Again, a very basic module in the Chemistry GCSE, but I just want to go through the topics as and when they come up. And yeah, so we'll eventually get to the kind of other topics eventually when I get them done. But yeah, welcome. Feel free, if you have any comments or questions at all, feel free to put them down below. I will try my best to answer, or maybe your fellow students will answer them for you, because they're usually a lot better at getting to the comments than I am. But yeah, feel free to, the classic, like, subscribe, all of that shebang, and let's just crack on. So starting off with chemical bonds. So we've got three types of chemical bonds: ionic, covalent, and metallic. Ionic typically takes place between metals and non-metals, where the electrons in the outer shell of the metal atom are transferred. So the metal loses its electrons, and which then are gained by the non-metal. So as a result of this, because the metal is losing the electron, because of the proton and electron charges, it becomes positively charged, whereas the non-metal becomes negatively charged because it's gained that electron. You can see a little diagram of it in, like, slightly above the table, where you can see NaCl has the sodium has lost an electron, which the chlorine has then gained. And this is the kind of the way you want to draw it as well in an exam. You want to make sure that you've got that dot cross kind of differentiation. Ions produced from groups 1, 2, 6, and 7 gain full outer shells of electrons, so they have the same structure as a noble gas. So to clarify that means that elements in group 1 will lose an electron, elements in group 2 will lose 2 electrons, and 6 and 7 will gain 2 and 1 electrons respectively. Electron transfer during the formation of an electrons transfer during the formation of an ionic compound and could be represented by a dot cross diagram. So just like I said in the little image above the table, that's kind of how you want to be able to draw it. Ionic compounds are joint structures of ions that are held together by strong electrostatic forces, so between the oppositely charged ions. And since the structure is 3D, the forces act in every direction. So basically what makes ionic bonding so strong is because that both attraction and repulsion between the positive and negative charges means that it's very tough, very strong bonds. Then we've got covalent. So covalent bonding is when atoms share one or more electrons. Common examples: polymers, HCl, so hydrochloric acid, hydrogen in its natural form of H2, and then CH4. Giant covalent structures consist of many atoms covalently bonded in a lattice structure. So an example of this is a diamond, and often represented as dot cross diagrams, ball and stick, or 2D, 3D diagrams. So you can see a dot cross again. Well, it's not quite dot cross, but it's a similar kind of idea. So imagine all the blue are crosses and the reds are dots, and that's how you'd want to draw it, basically. And then we've got metallic, which is our final type of chemical bond. So this is a bonding in metal consisting of positive ions, so basically atoms that have lost electrons, and then these delocalized electrons the positive ions in the regular pattern, but the delocalized electrons are just kind of moving around them. They don't have a set place for them, they just freely move, which makes a massive difference to their properties. The delocalized electron system consists of the electrons lost, and these are free to move through the structure and so are shared. And as these are shared, the metallic bonds are strong. So yeah. But how does the bonding and structure relate to properties of matter? So we've got 3 states of matter: solid, liquid, and gas, plus the bonus aqueous, and you've got the state symbols as well, which are useful to know. So you've got S for solid, L for liquid, and G for gas, plus aqueous, so AQ. The amount of energy required to take a substance from liquid to gas or solid to liquid depends on the strength of the bonds between particles in the substance. So the stronger the forces, the higher the melting and boiling points of the substance. Ionic compounds have regular structures, aka giant ionic lattices, in which there are strong electrostatic forces of attraction in all directions between oppositely charged ions. So essentially what we've just discussed. So because of these strong electrostatic forces between the ions, they have a high melting and boiling point, as a lot of energy is required to break these strong bonds. However, when melted or dissolved in water, these structures can actually conduct electricity, as the ions are freely moving and can carry charge. But as a solid, they're all fixed in place, so it cannot conduct electricity. So that's one really important thing to remember, is that ionic compounds can only conduct electricity when in a certain state. And you can again see the example of NaCl, sodium chloride here, where you can see how the actual 3D structure of it works. Then moving on to look at, so small molecules have low boiling and melting points, as they have weak intermolecular forces which are broken, not the covalent bonds within the molecules, but just the intermolecular forces within that. So although these forces do increase in strength as the molecule size increases, these do not conduct electricity, as they do not have an overall electric charge. Polymers have very large molecules, and the atoms are linked by covalent bonds. So an example here is ethene turning into polyethene to become its polymer. Intermolecular forces between polymer molecules are relatively strong, and so these substances are solid at room temperature. Giant covalent structures are solid with very high melting points. All the atoms are linked by strong covalent bonds, but can be overcome through melting or boiling. Examples include diamond, graphite, and silicon dioxide, also known as silica. So you can see a little diagram on the side, which is just diamond. That's how diamond looks in its 3D structure. And then moving forward to look at metals and alloys. So metals have giant structures with strong metallic bonding. Most have high melting and boiling points. But within a pure metal, the layers of atoms are able to slide over each other. So metals can be bent and shaped, which doesn't make them super useful for a lot of things. However, alloys are made from 2 or more types of metals. And because of the different sized atoms within these and being arranged in layers, makes it a lot harder for the atoms to slide over each other, creating a much stronger substance than pure metal. As you can see in the little picture below, you kind of see how this makes sense, because the pure metal is very uniform. It's very easy for the layers to slide over each other, but whereas in the alloy, it's got that different metal atom in there, and so that messes up that uniform pattern, and it can't slide quite so easily. Metal is a good conductor of electricity because the delocalized electrons in the metal carry electrical charge through the metal. So very similar to the metallic bonding that we looked at earlier. These electrons can also carry thermal energy, so metal is a good conductor of thermal energy / heat too. Then looking more specifically at carbon, the oh so wonderful carbon that is basically the foundation of a lot of chemistry and science. Each carbon is joined, so first looking at diamond, each carbon is joined to 4 other carbons through covalent bonding. Therefore, it's a very hard substance, has a very high melting point, and does not conduct electricity. Then we've got graphite, so each carbon is covalently bonded to 3 other carbons this time, forming layers of hexagonal rings which have no covalent bonds between the layers. The layers can slide over each other due to no covalent bonds between them, but weak intermolecular forces. So graphite is a very soft and slippery metal or substance. 1 electron from each carbon is delocalized, so similar to other metals, can conduct electricity. So where you see these layers here, in between them is just delocalized electrons, which can carry that electricity. Then we've got graphene and fullerene. So graphene is a single layer of graphite, has properties that make it useful in electronics and composites. It is very strong because atoms within its layers are very tightly bonded, and it is also elastic because the planes of atoms can flex relatively easy without the atoms breaking apart. Carbon can also form fullerenes with different numbers of carbon atoms. These are molecules of carbon atoms with hollow shapes based on hexagonal rings of carbon atoms, but they may also contain rings of 5 or 7 carbon atoms. Carbon nanotubes are cylindrical fullerenes with very high length of diameter ratios and are useful for nanotechnology, electronics, and materials. Examples of this is lubricants to deliver drugs in the body and working as a catalyst within chemical reactions. Nanotubes can be used for reinforced materials such as tennis rackets. So that is the lowdown on carbon, on diamond, graphite, and graphene. And now we are going to be moving on to nanoparticles, so the final kind of section of today's slideshow or YouTube video or whatever this is. So nanoparticles are 100 nanometers across. They contain a few hundred atoms. Nanoparticles are smaller than fine particles, which have a very small diameter as well. Coarse particles have diameters between these very small numbers and are often referred to as dust. As the side of cube decreases by a factor of 10, the surface area to volume ratio increases by a factor of 10. Nanoparticles involve fullerenes, but has different properties to the bulk chemical it's made from because of the high surface area to volume ratio. It may also mean that the smaller quantities are needed to be effective than for materials with normal particle sizes, so fullerenes have different properties to big lumps of carbon. Uses, so nanoparticles we use as catalyst because of their high surface area, which means we don't need to use as much as potentially other catalysts that have a smaller surface area. Produce highly selective sensors. Nanotubes make stronger, lighter building materials. Cosmetics such as suntan cream and foundation and things because it's able to produce it with no white marks. Lubricant coatings for artificial joints and gears. And nanotubes can be used in small electrical circuits for computers, although there is a slight disadvantage of the fact that they are potentially toxic, as they may be able to enter the brain from the bloodstream and cause harm. But, we will not know until 20 years in time when they start doing some research and realising, this ain't ideal. But anyway, slightly off topic there. But yes, that is today's video. I hope you guys enjoyed it. I hope you found it useful. Please let me know if you do have any comments or questions. And I shall try and get back to you. But I shall leave it there and see you next time. Bye.